Hey guys, it's Miss Johnson and I'm here to bring you our notes for chapter 8.2. This is the first part of section 8.2 in our book. Today we are talking about how to actually construct a confidence interval. In section 8.1, you learned what a confidence interval was and how we speak about them and what it's representing. Today we're going to actually talk about how do we find one of those confidence intervals? How do we construct them? So a couple of main things that I want to point out on this learning target slide before we get started is what we know we have to do. We have to state and check the random, we have to check the 10% condition, and we have to check to the large counts conditions before we can construct the confidence interval. Then we're going to determine a critical value. That's something we'll learn about today. Then we'll actually construct and interpret. There's that key interpret phrase, which means you're going to write out a statement, and then determine the sample size required to get a certain confidence interval. So really it was this first point that I wanted you to kind of see. Before we can even construct a confidence interval, we have to check these things. Is it random? Does it fulfill the 10% condition? And does it fulfill the large counts condition? So what we are looking at is a one sample Z interval for a population proportion. The reason it is called a Z interval, if you think about Z should hopefully bring up to you Z-score. So if you're thinking about a Z-score, Z-scores are only applicable when we are looking at normal curves. So a normal curve is one of the things that we have to know is true before we can actually calculate this confidence interval for a population proportion. Now, the other thing about Z is the Z interval is going to go with a proportion. So we're dealing with proportions in this chapter, in chapter 8. We're going to get to confidence intervals of means later in chapter 10, but right now we're dealing with confidence intervals of proportions. So here's your formula. This is the formula for actually calculating that confidence interval. You have your p-hat value, whatever your p-hat value is from your sample. Then there's the plus and minus. You probably remember plus and minus from the quadratic formula or maybe other things, but plus and minus just means that you are moving up from the proportion and down from the proportion. You're going to add some value and you're going to subtract some value, and that proportion is going to be in the middle. And your proportion comes from this. You've got a critical value, a Z star, which we'll talk about how to find, times the square root of p hat times 1 minus p hat, all divided by n. And if you remember that little piece of the formula, that little formula right there comes from the standard deviation of a proportion. So that should mean something to you. Obviously, we know that standard deviation means that that's the typical distance we move from the mean. So if our mean proportion, or our p hat, we have to take our standard deviation away from that. It's not simply just the standard deviation. It's going to be the standard deviation times this critical value. And this is what gives us the C percent of confidence, depending on what confidence level we're looking at. Are we looking at 90%? Are we looking at 100%? Not 100, but 90, 99, 80. Sometimes they go as low as 80. That's where that Z star value is going to come into play there. So this is just a little bit more details of what those three parts are. The challenge or part of constructing a confidence interval, we can't just simply take all these values and plug them into the equation. Before we are allowed to take them and plug them into the equation, there are three conditions that we have to make sure are met for this formula in order for it to be valid. So the first condition comes from the random condition. We need to make sure that our p-hat is a valid point estimate and that it was taken from a random sample, okay? We just need to make sure that randomness was used, okay? This isn't an incorrectly sampled sample. This doesn't have bias in it. It needs to be a random sample. So that's how we know that we can use that valid p-hat value. The second condition that we have to verify in order to be able to calculate a confidence interval is the large counts condition. The large counts condition is met, if the large counts condition is met, then we can use normal distribution to calculate that critical Z star value. So we don't know the actual value of P. Since we don't know the actual value of P, we need to use the large counts condition, meaning n times P hat is greater than or equal to 10, and n times 1 minus P hat is greater than or equal to 10 to be allowed to use that P hat value. It's almost impossible to know the actual proportion, but if we use the large counts condition, then we're allowed to use P hat. If we're allowed to use P hat, then we're allowed to find the Z star value for that P hat value. And then the third one is that 10% condition. And we've talked about the 10% condition before. When we are sampling without replacement, which is almost always, when you're dealing with people, even when you're dealing with animals, you usually don't put your subject back and then be allowed to pull them again for your sample. Once you pull someone for a sample, you're not going to pick that person again. So you're sampling without replacement. If you're sampling without replacement, in order for it to use normal calculations, you have to have the 10% condition be met, which means that your sample size is less than 10% of your population. So we will be checking all three of those conditions before, keyword before, you calculate the confidence interval. So that's a big piece that you have to show on the AP exam. Before you calculate the confidence interval, you have to check those three conditions. You have to state that it was random, you have to state that it fulfills the large counts condition, and you have to state that it fulfills the 10% condition. Once those three things are met, then the next thing you're going to look for is the standard error of the statistic. So it says, when the standard deviation of the statistic is estimated from data, the result is called the standard error of the statistic. So the conditions for constructing a confidence interval about the proportion, we talked about this, random, 10% condition, large count condition, all of those things must be true before we can find that standard error. All right, so let's just talk about checking the conditions. So in this example, it says Mr. Buckley's class wants to construct a confidence interval for P equaling the true proportion of red beads in a container, which includes over 3,000 beads. Recall that the class's sample of 251 beads had 107 red beads and 144 other beads. So this comes from an example that was in the book on a previous day, and we're just going to refer back to this data. So there was a bucket that had 3,000 beads in it. The class pulled a sample, and in the class's sample, there were 251 beads, and 107 of them were red, 144 were other colors. So check if the conditions for constructing a confidence interval for P are met. So here's your three conditions. Number one, random. Okay, so we're looking at Mr. Buckley's class. Mr. Buckley's class took a random sample of 251 beads. So that is all you need to state for the random condition to be met. Mr. Buckley's class took a random sample of 251 beads. If you want to look back at where this example came from, in your book, they talk about this back in section 8.1 on page 537. Page 537. They talk about Mr. Buckley's class there in the beads example and the 251 beads that they pulled. So, random sample. Mr. Buckley's class took a random sample of 251 beads. Good, check. First condition is met. Second condition. Second condition is the 10% condition. Let's talk about that one. Now, it really doesn't matter what order you list these in. It does not matter. They just all three have to be stated. So the 10% condition, for this one, I would say that Mr. Buckley's sample of n equaling 251 is less than 10% of n being 3,000. Okay, so state somehow that you know that the 251 is going to be less than 10% of 3,000, which it's true. 10% of 3,000 would be 300, and 251 is less than that. So good, 10% condition is met. Great. The next one is large counts condition. Large counts. And this is where we would show, so we've got the proportion. We're using the p hat values here. So we need to show that n times p hat is greater than or equal to 10, and n times 1 minus p hat is also greater than or equal to 10. So in this case, that's 251 times your p hat value, which the red beads is 107 out of 251, which is equal to 107, which is greater than or equal to 10. Great, check. The n times 1 minus p hat would be 251 times the other proportion of beads, 1 minus 107 out of 251, which is equal to the 144. That's the 144 others. Also greater than or equal to 10, check. Okay, so this whole thing right here, it's a lot. There's a lot to list out, but all of these things right here have to be checked and listed and verified before you can even calculate the confidence interval. You can't do the confidence interval until you actually address all of these things. Okay. So now let's talk about the critical value, because once we've established our conditions have been met, then we can get into finding the critical value. So how do we get that critical value? Well, that z star value comes from our normal curve. So what we are looking for is to find the critical value for z star for a 95, they're just using 95% here. For a 95% confidence interval, it starts by labeling the middle 95%. So if I'm labeling the middle 95%, that means that I have 2.5% on either side. So check out the area here. If the area in the middle is 95%, if that's what I want for my confidence interval, okay, I've got the p hat in the middle, and sorry, that was a bad hat. P hat in the middle, and I want an interval to go out in either direction, to the left and to the right, that covers 95%. That means that I have 5% left over. Well, we know normal curves are symmetrical. So when I take 5% and divide it in half, I get 2.5%. So there's 2.5% on either side of the curve. Since there's 2.5% on either side of the curve, I know that that's the area that I'm looking for. So when I go into my table A, I can get a z star value by looking at what has 0.025 to the left. I'm basically looking at this. What has an area of 0.025? Now, you get a z-score of negative 1.96. We don't use the negative because we know that the curve is symmetrical, so we know that this is positive 1.96. So you're going to use a z-star value of positive 1.96. Okay, I know that seems kind of tricky. Like, how do we get to just drop the negative? Well, the fact that the curve is symmetrical is how we get to drop the negative. Because when we look at table A, we're looking at everything measuring to the left. So I'm looking at this bottom 2.5%, but I don't want the negative in front of my z-star, so I'm going to use the positive because that gives me the top 2.5%, which is the same amount of area. Now, if you're using technology, which I think is what most of you do, when you go into your TI-84, you use inverse norm, and then you can type in your area of 0.025. Your mean is going to be 0, and your standard deviation is going to be 1, because we are looking at this as a standard normal, capital N, curve. Standard normal curve always has a mean of 0 and a standard deviation of 1. So that's what you would type in. You just get your area, and then you type that in. It's going to give you a z-score that is negative. But again, we know that normal curves are symmetrical, so we know that we can use the positive version on the other side and have the same amount of area. So we just drop the negative and use the positive of 1.96. So now let's put this into practice. So next example here, it says, according to a 2016 Pew Research Center reports 73% of American adults have read a book in the previous 12 months. This estimate was based on a sample of 1,520 American adults. Assume the conditions for inference are met. Hey, check that out. Assume the conditions for inference are met. That's really good. What that means there is that they've checked those three things for you. They've done random, they've done 10%, and they've done large counts. Okay? That's what they're saying there. Check, check, check. So when you are told that the conditions for inference are met, then your conditions have already been checked. So in part A, it says determine the critical value for a 90% confidence interval for the proportion. All right, so let's talk about confidence intervals and 90%. So here's my normal curve. If I want the middle 90%, that means I've got 10% outside. That means that either side is going to be half of that, which is 5%. Okay, so then in your calculator, you're going to go to inverse norm, and you're going to have an area of 0.05. You're going to have a mean of 0 and a standard deviation of 1, and see what that gives you. So I'm going to my calculator, I go to second distribution, I go to inverse norm, which for me is option 3. You go to 0.05 for your area, mean is 0, standard deviation is 1. Now I have an option to pick a tail. You could pick the right tail if you wanted. If you pick the right tail, it's going to give you the positive value. If you don't have an option to pick which tail, if you're looking at the left or the right, it's going to give you the left tail, which is going to be the negative value, and then you know you just need to make it positive because of that property of symmetry. So I get here negative 1.645 for my Z star value. So I end up with Z star being, and I'm going to use that positive version, so Z star is equal to 1.645. Okay, so there's my critical value. Next, now I need to actually plug it into the equation. So in part B, it says construct the 90% confidence interval for the proportion of all American adults who have read a book in the previous 12 months. So for B, now I'm going to use that equation. So I have 0.73 plus or minus my Z star value, 1.645 times the square root of, there's this standard deviation piece, so 0.73 times 1 minus 0.73 divided by my square root of n, which in this case my n is 1,520. So I've got that for my equation. I like to do this in pieces in my calculator, so I'm going to start with just the radical. In my calculator, I'm going to take 0.73 times 1 minus 0.73. I end up with 0.1971. I'm going to divide that by 1,520. I get a scientific notation here, but that's okay because I'm going to immediately take the square root. So I've got 1.2967 in times 10 to the negative fourth in my calculator. That's probably what you're seeing. That e to the negative 4 is that scientific notation part. Now, just go ahead and take the square root. You don't need to retype this. So if you do second square root and then second answer, which is down at the bottom of your calculator above the negative sign, then you've pulled that previous answer without needing to retype it, because retyping that scientific notation is kind of a pain. So I'm just going to pull my previous answer and I'm going to hit enter. And that radical ends up being 0.73 plus or minus 1.645 times 0.01387, and it keeps going. Okay. I'm leaving that in my calculator. Again, the second answer button is your best friend here. I'm not going to retype it. I'm not going to truncate it off. I'm not going to round it. I'm just going to leave it right like it is. I need to take that and hit times 1.645. So then that gives me 0.73 plus or minus this decimal of 0.01873 ... keeps going. Here's where it splits. So I need to take 0.73 plus that whole decimal, 0.0187 ... and 0.73 minus 0.01873 0.0187 dot, dot, dot. So I'm subtracting one and I'm adding the other. So 0.73 plus second answer. Again, I use that second answer button as much as I can. So my upper value, because I added first, was 0.7487. And then if I do 0.73, now in my calculator, I'm allowed to arrow up, which is helpful. I'm going to arrow back up to that answer and just pull it. So 0.73 minus, arrow up, hit enter on the answer I want from that multiplication of the 1.645. And I get a lower bound of 0.71126 dot, dot, dot. So here's where you're going to round. This is where it's going to be a lot easier for you to actually round these things when you can. So I end up with an interval of 0.711 up to 0.749 roughly. So that's what my confidence interval looks like. Okay. Now, in part C, I have to actually go through and interpret. So I'm going to interpret this. I'm going to write really small here, and I apologize for that because I always run out of room on these screens. But this is what my interpretation would look like. Here's all the points that it needs to include. We are 90% confident that the true proportion of American adults who read a book in the last 12 months is in the interval, or you could say is between 0.711 and 0.749. Okay, again, I wrote that really, really small, and I'm sorry about that, but here's all the points that it has to include. It has to include the confidence level. It has to talk about how it's the population proportion. So when I say true proportion, I'm talking about the population proportion. Or you could even say that the population proportion, something along that line, give it the context. That's the reading the book in the last 12 months, and then actually list what the interval is. Those are all the parts that it has to have when you write out your interpretation. Okay, that's going to take us to the end of the first half of this section. So we're going to take a break here, and we'll come back in our next lesson video to talk about the second part of 8.2. Thanks for tuning in, and I will catch you next time.